Hey there, physics friends. At this point in your work on relativity, you've probably been puzzling over different questions, running up against dead ends, convincing yourself of one answer, and then convincing yourself that that answer is wrong, and so on. And as you work through these problems and you struggle with them and you practice them, you're developing an understanding of the content, and that understanding becomes durable and deep when you actually have the chance to practice this extensively. And I think it's often the case that when you're in this kind of state of confusion, that's when a lot of the learning happens. And historically with relativity, people have kind of tested their understanding by coming up with situations that seem to be contradictory or have different outcomes in different frames. And if they're able to kind of resolve that tension between the two frames, then they often kind of come to a deeper understanding of the content. So this idea of using paradoxes in relativity as an understanding and a teaching and a learning tool has been going on for many, many years. And we're going to explore a few of those in this class as well. Of course, the goal here is to recognize that the paradox is just an apparent paradox. What do I mean by that? Well, a paradox is a statement that seems contradictory or unbelievable or absurd, but that actually might be true in fact, or is true in fact. And that's kind of what we're after here. We're going to do a situation. We're going to analyze a situation in one frame, and analyze it in another frame, and convince ourselves that, strange as the outcome may be, that is in fact what is predicted and what is stated in relativity. So in a subsequent video, we will look at a situation where it looks like an object will get sliced and cut in one frame, but in another frame it looks like it will not, and so we have to resolve that tension by doing a proper full analysis. Here I just want to introduce this idea of working through paradoxes using the case of time dilation, right? So what we're told in relativity is that a moving clock ticks slow, more slowly than a clock that's at rest. But we're also told that all frames of reference are equally valid. And so this leads to the common source of confusion, which is, okay, let's take the situation to be explicit. Let's draw a little picture here where we have Bob at rest on the ground. What Bob is wearing, that's weird. Why did I draw it that way? No, I meant to draw arms. Okay, Bob is at rest on the ground, and Alice is in a rocket ship moving at high speed to the right. Okay, and so we have these two frames of reference, and let's say in Bob's frame, he's saying, okay, my clock is at rest, Alice's clock is moving, therefore Alice's clock will tick more slowly than mine. And then in Alice's frame, she would say, I'm Alice, I'm at rest, and Bob is moving, therefore his clock ticks more slowly. So how is it that if Alice's clock ticks slowly for Bob, then how could it be that Bob's clock ticks slowly for Alice also at the same time? In other words, if my clock runs slow to you, then how can your clock run slow to me? That seems impossible and contradictory. So let's explore how we can explain it in a very rational and clear way. A common theme in these paradoxes in relativity is that somebody doing the analysis will remember or include time dilation and remember or include length contraction, but they will often forget the relativity of simultaneity. In other words, they will often forget that moving clocks are not in sync, that the rear clock is ahead by L naught V over C squared. So let's see how this plays out in the problem of the rate that clocks tick. So let's set the problem then. We have Bob at rest on the ground, and Bob is allowed to put as many clocks down as he wants. For now, we just need to have two of them. We'll have B1 and B2, Bob's two clocks, and then Alice in her rocket is flying to the right. And rather than drawing the rocket every time, I'm just going to draw the clock as a moving clock, okay? We're going to have Bob's clocks be separated by a distance d, and Alice and her clock be moving in this frame with velocity v. Okay, so we're going to start out by saying that Alice and Bob's first clock are set to read 0 this instant that Alice passes Bob's first clock. Okay, and because B2 is at rest on the ground, we know that the reading on B2 is going to be 0 as well because it matches the reading on B1. Okay, great. So this is the first event, and then the next event is going to be when Alice reaches the second clock, B2. So let's take a look at that. Good, so we see now that clock A, or Alice, is over next to B2, and we want to kind of put some numbers in on these clocks. Well, the first thing we notice is that Alice has traveled a distance of d at speed v, and so we know that the elapsed time will just be d over v. So since the clocks at rest indicate the elapsed time, we know that both of these clocks read d over v. Okay. What about Alice's clock? Well, by time dilation, Alice's clock is a moving clock, and so it's going to tick less than d over v by a factor of gamma. Remember, delta t moving is less than delta t rest by this factor of gamma. In this case, Alice is the moving clock, Bob's at rest. Delta t for Bob was d over v, and so delta t moving will be d over gamma v. So we can put that in to Alice's clock. Okay, so from this point of view, in Bob's frame, the ground frame, it is indeed true that Bob's clocks tick more than Alice's by this factor of gamma. So the question then is, how is it that in Alice's frame, it's going to be the case that Bob's clocks tick less than Alice's clock? Because in Alice's frame, Bob's clocks are moving, so they should tick less than Alice's clock. But how can it be that Bob's clock is going to read a larger number than Alice's clock in both frames if Bob's clock is going to tick less than Alice's clock in Alice's frame? So let's take a look at the other frame and see what we see. Okay, so here's the diagram in Alice's frame. Again, this is the instant that Alice's clock lines up with B1, and we said by definition that we were going to set those clocks to read 0. Okay. Now, the next picture is going to have B2 arriving, so let's take a look at that. And indeed, here we see clock A in the same place as it was in the previous picture, and now clock B2 has arrived. Let me label that. And B1 is off on the left. And the question is, okay, well, what is the reading now on the various clocks? Well, one thing we know is that in order to arrive at A, B2 has had to travel a distance d over gamma, and it's traveling at a speed v, so the elapsed time is simply the distance divided by the speed. So it's d over gamma, all divided by v, or d over gamma v. The elapsed time is the time ticked off on the clock at rest. Well, that's A's clock, isn't it? Because we're in A's frame. So just as before, we see that clock A reads d over gamma v when B2 aligns with A. That's still true. But the claim is that in this frame, in Alice's frame, B2 is a moving clock, so it's going to tick less than A has ticked. Indeed, by time dilation, B2 will tick less than A by a factor of gamma. A has ticked d over gamma v, so B will have ticked d over gamma squared v. So the question then is, how can clock B2 read d over v if it's only ticked d over v gamma squared? Okay, where remember, gamma is bigger than 1, so if we're dividing by gamma squared, we're going to get a smaller quantity. So this d over v gamma squared is less than d over v. So how can B2 read d over v if it's only ticked off less than A ticked off? And the resolution to that paradox, of course, is that B2 did not start with a reading of 0. So it can get all the way to d over v, even though it's only ticked less than A has. And that's because of the rear clock ahead. Most of the paradoxes, as I said before, most of the paradoxes arise because people forget the rear clock ahead part. They'll remember length contraction, they'll remember time dilation, but often the RCA goes unnoticed. Okay, so we are going to put in here the RCA. Remember B2 in the first picture by rear clock ahead is going to read L naught V over C squared ahead of the first clock, which is reading 0. But L naught here is the rest length separation between the clocks, so that's D. V we'll just leave alone, and C we just leave alone. Okay. So again, the claim is that D times, that the final reading on clock B2 is the initial reading plus the amount of time ticked off. Right? So the initial reading is what it was in the first picture, and then we agreed that it ticked off D over V 1 over gamma squared amount. Okay, and the claim is that this quantity equals D over V, which is the reading that we found in the ground frame. Okay, and it may be surprising perhaps, but oh, look, I've made a mistake. This first term should be dv over c squared. I dropped my c squared, I just didn't copy it down from this equation up here. Okay, so we can play this game by first factoring out a d over v, which leaves us with a v squared over c squared plus a 1 over gamma squared. And if you recall, a 1 over gamma squared is just 1 minus v squared over c squared. Remember, if you have a 1 over gamma squared, you should rejoice, because that's a nice clean quantity, easy to work with. So we have d over v, v squared over c squared, plus 1 minus v squared over c squared. And lo and behold, the v squared over c squared terms cancel, and we are in fact left with a d over v. So the bottom line is that clock B2 can get all the way to d over v, even though it ticked only gamma squared times less than that. And it does so because it didn't start at 0. It started at dv over c squared. And so at the end of the day, the reading on this clock will be d over v, whether you do the analysis frame or the ground frame. So that's an example of an apparent paradox. How can Alice's clock tick slow relative to Bob, and simultaneously Bob's clock tick slow relative to Alice? Well, there's no contradiction here at all, as long as you account for all of the 3 of the relativistic effects: time dilation, length contraction, and don't forget, rear clock ahead. Okay. In subsequent videos, we'll look in more depth into other related paradoxes, but this is kind of a fun one that we can do. And the next one that we'll talk about is similar to but different from the pole and the barn paradox. Until next time, be well and take care.